Drop it.
Even before Isaac Newton's day, apples fell. Always downwards, never upwards. No one thought about it. That's the way things were. The Englishman, Isaac Newton, did think about it. Why, he asked, does the apple fall vertically downwards? What force is pulling it? This question led Newton to develop the idea of gravitation as a universal force. It became the basis of one of the most important scientific works of all time. The Philosophiæ, Naturalis, Principia, Mathematica, the mathematical principles of natural philosophy. The movements of the heavenly bodies have fascinated people since time immemorial. What rules govern these movements? In the 6th century BC, there lived in Greece a philosopher named Anaximander. He taught that the earth was a disk in the center of the universe. The fires of hell burnt within it, and the vault of heaven was stretched above the earth. Above this vault were more fires, but there were holes in the vault, through which we could see the flames. These holes were the stars. By the time of the astronomer Claudius Ptolemy, who lived in the Egyptian city of Alexandria in the 2nd century AD, things had progressed somewhat. He too saw the Earth as the center of the universe, but the sun, moon and planets were attached to solid but transparent spheres which moved around the Earth. This model allowed astronomers to make fairly exact predictions regarding eclipses of the sun and moon and future positions of the planets. It is curious that a theory could be wrong and yet lead to largely correct results. It was over 1,000 years before a Polish cathedral canon named Nicholas Copernicus ditched the notion that the Earth was at the center of all things. In the 16th century, he came up with the idea that the planets moved around the Sun and that the Earth was one of these planets. But Copernicus was unable to prove this theory. At the start of the 17th century, more exact observations and the discovery of mathematical laws allowed the German astronomer Johannes Kepler to refine the Copernican model. Kepler established that the planetary orbits around the Sun were not circles but ellipses. He noted that a planet moved fastest when its elliptical orbit took it closest to the Sun. What he didn't know was what kept the planets moving at all. On the 4th of January 1643, Isaac Newton was born in the village of Woolsthorpe in Lincolnshire in eastern England. His father, a farmer, died before he was born. His mother intended him to take over the family farm, but little Isaac was not cut out to be a farmer. For hours at a time he would gaze out over the water while the sheep just wandered away. He preferred to sit in his room and decorate the walls with drawings of all kinds. Luckily for him, he was not forced to continue in his rustic existence. His uncle, a clergyman, enabled him to attend the grammar school in the nearby town of Grantham. He lodged with the family of an apothecary, a friend of the Newtons. There he learnt to identify various medicinal herbs and was soon allowed to mix herbal remedies himself. At the age of 18, Isaac Newton matriculated at Trinity College in the University of Cambridge in order to study mathematics and philosophy. A few years later, he was appointed Professor of Mathematics at Cambridge, but his interest ranged far wider. Newton concerned himself with a wide range of physical and chemical phenomena, and he himself built the instruments he needed for his research. Using his reflecting telescope, he observed the movements of the planets in the night sky. What could it be, he asked himself, that kept the planets in their elliptical orbits? The natural philosophers, as scientists called themselves in those days, discussed various models which might explain the phenomena. One Englishman, William Gilbert, thought the movements of the celestial bodies were due to invisible and intangible magnetic forces. The French philosopher René Descartes preferred a different explanation. He thought the whole universe was full of material particles. The planets, he suggested, were caught up in this swarm of particles like leaves in a whirlpool. There was a young English astronomer who thought they were both wrong. Edmund Halley had been trying to formulate a theory of planetary motion for years, but a solution escaped him too. In August 1684, he visited Cambridge, where he met the 41-year-old Isaac Newton. Maybe, or so he hoped, the celebrated professor of mathematics would be able to give him a little help. Halley assumed that there must be some central force keeping the planets in their orbits. For Newton, this idea was nothing new. Many years before, while he was still a student, Newton had considered the problem. And without apparent effort, he had come up with a mathematical proof of this force and its effects. But he had never published his results. In fact, he'd almost forgotten them. Halley realized the importance of Newton's work and urged him to set out his theories in a major scientific publication. Newton agreed, and shortly afterwards started work on the Principia Mathematica, the mathematical principles of natural philosophy, a 3-volume work whose publication Halley financed 2.5 years later. Among other things, this work contains the 3 laws which form the basis of classical mechanics to this day. Newton's first law states that a body at rest will remain at rest unless acted upon by external forces, and a moving body will continue to move at the same speed and in the same direction. Newton's second law says that a force acting on a body will give it an acceleration proportional to that force and in the same direction as the force. Put another way, force equals mass times acceleration. His third law relates to action and reaction. If one body exerts a force on another, the latter will impart an equal and opposite force to the former. It is this reactive force that brings the ball to a halt and makes the boat glide back. Regarding his third law, Newton made the prophetic statement that it was the principle that would enable men of future days to fly to the stars. The principle in question was the recoil effect, which propels the rocket into the sky. Hot gas streams out of the exhaust, ensuring that the spaceship moves in the opposite direction. Isaac Newton decided that bodies moved because they were subject to external forces. Using the moon as an example, he showed that it could only stay in its elliptical orbit if the Earth attracted it. Opposed to this attractive force is the centrifugal force, which ensures that the moon does not crash into the Earth. The name given by Newton to the attractive force was gravitation. Using the orbital speed of the moon and the attractive force exerted by the Earth, Newton was able to prove mathematically that centrifugal force and gravity keep the planets in their orbits. However, Newton was not content with this. If the Earth's gravity can keep the moon from leaving the Earth, can the Sun's gravity, he wondered, keep the Earth in its elliptical orbit? And can Jupiter's gravity keep its moons in their orbit? If the answer was yes, then gravity would be a universal property of anything with mass, and it would explain the movements of all the heavenly bodies. And so it was that Newton formulated his universal law of gravity. Knowing the masses of 2 bodies and how far apart they were, he was able to calculate the gravitational attraction between them. He was now able to make exact predictions of the movements of the celestial bodies. Using his discoveries, astronomers in later centuries were able to find hitherto unknown planets in the solar system: Neptune and Pluto. Newton's law of gravity provided the definitive mathematical support for the Copernican system. And more earthly phenomena could be explained too. The apple falls vertically to Earth because of gravity, and the only reason it falls faster than a feather is because the feather is so light it floats in the air. The gravitational principle also allowed Newton to explain the tides. They are the result of the moon's gravity acting on the waters of the oceans. Newton's law of gravity is still the basis of classical physics even today, admittedly relativized somewhat by further discoveries in the early 20th century. The work of Albert Einstein revolutionized our view of the universe. He threw out Newton's notion that time and space were independent of each other. He even went a step further and showed that gravity also exerted an influence on time itself. On a large, massive planet, time flows more slowly than on a small, light one. Newton described gravity as a force between two bodies. Einstein saw it as a property of space-time. In the presence of a massive body, space-time changes. As a result, Einstein's gravity works not only on material bodies, but even on electromagnetic waves, including light. Einstein's theory was confirmed just a year after publication. During the 1919 solar eclipse, astronomers observed a distant star close to the Sun. As Einstein had predicted, its light was deflected by the Sun's gravity. But the changes Einstein made to Newton's theory only come into play on a cosmic scale, with strong gravitational fields and high velocities. For everyday purposes, Newton's law of gravity is entirely adequate. At the age of 50, Newton gave up his scientific researches and moved to London, where he became Master of the Royal Mint. He ran a vigorous campaign against counterfeiters. In recognition of his scientific achievements, he was knighted by Queen Anne in 1705 at the age of 62. Sir Isaac Newton died in London at the age of 84. He was buried in Westminster Abbey. Today, Sir Isaac Newton is seen as one of the most important scientists of all time. He is esteemed not only as the founder of classical theoretical physics. Modern acoustics and aerodynamics owe a great deal to his work. And in optics, he was the one who recognized that white light is made up of the colors of the spectrum. He also discovered what are now known as Newton's rings, a characteristic feature of the diffraction of light. For all his success, he was aware of the limitations of his scientific knowledge. In his notes, we find the following sentence:
I do not know what I may appear to the world, but to myself I seem to have been only like a boy playing on the seashore, and diverting myself in now and then finding a smoother pebble or a prettier shell than ordinary, whilst the great ocean of truth lay all undiscovered before me.